Hello, my people. How are you? We are going to talk about light today. Um, so light uh, has sort of like a dual nature, and so the it it's partly a particle and partly a wave. But the particles that make up light are called photons. Photons are the particles that make up light. The nature of light, as I said, is a dual nature. Part particle, part wave. Okay, um, so that's sort of like the smaller that an object is, the more wave-like tendencies it exhibits. For example, an electron is a very, very small particle, and an electron behaves a lot like a wave, like a transverse wave. So, um, light travels in straight lines. So if you have like the light coming from the sun, that's not a spider; it's the sun. And you'll see that light travels in straight lines from all directions. Okay, so light travels in straight lines. We call those straight lines rays. And then light is extremely fast, super fast. So the speed of light, we call the speed of light c, is equal to 3 times 10 to the eighth meters per second, which is really, 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 really fast. That's fast enough to go around the world in 8 seconds. Okay. And then, okay, obviously, light allows us to see. We see everything on the visible spectrum. Um, and we'll talk about what the visible spectrum is in a second. And obviously, the speed of light is equal to distance over time, or oftentimes, as I said, c is equal to d over t. C is just the speed of light, which is 3 times 10 to the eighth meters per second. We often use c as the symbol for specifically not just any speed, but the speed of light. Reflection. Um, reflection is when light bounces off of some surface. Um, okay, you see reflection all the time. You can see reflect your own reflection in a mirror. You can see your own reflection in water sometimes, and even like um, shiny objects like aluminum foil. There's a lot of reflection of light going on in aluminum foil. And refraction. Refraction is when light waves pass from one medium to another. And bend. Okay, so if you've ever put your straw, if I don't have a straw with me right now, but if you put, oh, I actually do. Let me fill this up with some water. Give me 1 second. Sheesh. Okay. So if you look at the straw, ooh, it's sort of in an inconvenient spot. 1 sec. One more sip. If you look at the straw, it sort of looks like the position where the straw is in the water is a little off compared to where the straw is above the water. That's because when we see the light from this part of the straw here has to go from water to air, and it refracts as it gets to our eyes. So sometimes when you see something dipped in water, it looks a little off kilter. That's because the part that's in water has to go from the water to the air to your eyes. So when it goes from the water to the air, it bends. And then diffraction is when when light spreads out after passing through some opening. Okay, so you have some light ray and it passes through some slit. So like if you left the door open and light went through the door, you would see that after the opening in the door, the light is sort of spreading out after that. And that's diffraction. So you have the light going in every direction after it passes through some sort of opening. Light is an electromagnetic wave. Light is an electromagnetic wave. And what that means, it's part electric and part magnetic. And essentially what that allows it to do is it can travel in a vacuum. We know that light can travel in a vacuum because we can see the sun, right? The electromagnetic spectrum, okay? So the electromagnetic spectrum is a range of frequencies of electromagnetic waves. uh, we give different ranges different names. So, for example, number one, you have radio waves. Ooh, what did I just do? Radio waves. Number two, you have microwaves. Number three, you have infrared waves. Number four, you have visible light. Then you have UV rays, X-rays, and lastly, gamma radiation. Okay. In this is in order of increasing frequency. So if it's an order of increasing frequency, it must be an order of decreasing wavelength. And if it's an order of decreasing wavelength and increasing frequency, then it's an order of increasing energy. So, for example, if we're exposed to radio waves all of the time. They're all over the place. Um, and they're not that dangerous because they're not that high energy. If you're exposed to gamma radiation, like they were in Chernobyl in the meltdown, the nuclear meltdown in Ukraine, um, many people were exposed to gamma radiation, and they um, they developed cancer. They developed really terrible burns on their skin. So what a fun thing to talk about, Mr. Moshe. Thank you so much. Um, so the infrared waves are frequencies just below the visible spectrum. And the ultraviolet waves are frequencies just greater than the visible light. Visible spectrum, visible light. Spectrum just means all of the visible lights, all of the colors. Okay. And the different colors of light. So if you remember the mnemonic, most people should, Roy G. Biv. I think most people have probably heard about this, but maybe not. So Roy G. Biv is red. This is in order of increasing frequency as well. So each color has its own frequency. Thus, each color has its own wavelength because the speed of light is constant. The speed of all electromagnetic radiation is constant. So radio waves travel at the same speed as light waves. Okay. So Roy G. Biv, the longest wavelength is red, then orange, then yellow, then green. Oh, I should be, come on. Mr. Moshe, you have the opportunity to use some colors. Why don't you use some colors? Sheesh. Red, orange, yellow, green, blue, indigo, and violet. So your cooler colors here, if you see your cooler colors, um, this is the cooler colors are going to be your higher frequency colors. Okay. So maybe the president was talking, he said the other day, maybe we should just shoot the body with super high energy light. Maybe he was talking about blue light. Maybe you just shoot the body with blue light. I don't know. But when we see colors, the way that we can differentiate colors is that our eyes can differentiate different wavelengths. Okay. So when we see a color, it means that that color's wavelength is being reflected off of an object. So, let's think of an object. How about Maya's ice cream cone here? This thing is green. Okay, this is green. A green object absorbs all other colors but reflects green. Okay? So a green object absorbs all the other colors but reflects green. And that's what allows us to see green, because this object is reflecting green. It's absorbing red, absorbing yellow, absorbing blue, it's absorbing orange, but it's reflecting green. And that's what allows us to see the green. So are green objects really actually green? No, they just reflect green. Okay. So light from the three additive primary colors may be combined to make any color. Now, this is different than painting or coloring. Because when you're painting and coloring, you're talking about those colors absorb all other colors except the whatever color the crayon is. Okay, so a green crayon, like I said, absorbs all other colors except for green. Now, in this case, we're talking about actual light itself. We're talking about light coming from a source. So that light is actually that color, you know? So it's not the same as some object that's reflecting that light. We're talking about the light itself. Okay. And so the three additive primary colors are red, blue, and green. Okay, so if you combine these three colors in different ways, then you can get new colors. Okay. The visible region consists of spectrum of wavelengths from approximately 700 nanometers. So 400 nanometers to 700 nanometers. 400 nanometers to 700 nanometers. Okay. Yellow-green light is the brightest part of sunlight. Is white a color? Now, when light comes from the sun, it's white. Okay, and the light that comes from the sun it's the combination of all of the colors. Okay, now when you have light coming from the sun, that is every color in the visible spectrum is contained in that light. Okay, now what happens is the blue frequencies in that light get scattered when they hit the atmosphere, and that's what causes a projection above the earth of this blue, which is the sky, right? That's why the sky is blue, because when blue light hits the atmosphere, it scatters. It goes in every direction. You could say it's like diffraction, right? So mixing colored light. When only red and green light overlap, yellow is produced. Okay, so if I have green light and I have red light, I'm going to end up with yellow. Okay, when red and blue light overlap, if I have blue light and I have red light, I'm going to end up with magenta. Magenta. Okay, and then when you have green and blue light, you get this really cool color that I really like. It's called cyan. And I don't really have a cyan here. One second. I maybe do. Here it is. Cyan. It's called cyan when green and blue light combine. Okay, red, green, and blue are called the additive primary colors. The additive primary colors. Okay. So when you have in your television, your TV is just mixing all different frequencies at once to give you whatever the desired color of light is. All right. Complementary colors. Each color has a complementary color that, when added to it, will produce white light. So if you shine this color light and these two colors of light at each other, they'll produce white. Okay, so that's yellow and blue. So this is gonna forget everything you know about primary colors, but it's different because we're not talking about something absorbent. We're not talking about an object that absorbs all the colors except for the one it reflects. We're talking about the light that is truly just that one color. It doesn't absorb anything. So And then magenta. Ooh, sneak an A in there. Magenta and green, magenta and green. And then lastly, we have red and cyan. And this makes sense because if you think about it, right? If the three additive primary colors are um, are going to create white light. All when you have red, blue, and green together, that's going to create white light. So yellow is red and green and white. Red and green and blue, I mean. And then magenta we know is red and blue, and then you add green and you're going to get white. And then if you have red and then you add cyan, that's going to be red and then blue and green. Okay. So that's just what we're doing here is we're just adding all of the three colors up. And then lastly, we have a couple of just a couple of terms that refer to how light travels when it hits a certain surface. So, so some surfaces are transparent, and a transparent surface means light can pass through the object. Okay. And then some surfaces are translucent. Translucent. That means light will be blurred but can pass through. Okay. And then opaque means light cannot pass through. And a light ray, we already talked about this, is a beam of light. Example of transparent glass. Okay. Translucent water. Sunlight can pass through water, right? But it gets a little blurry. And then opaque would be like most objects, like a rock. Okay, so just to review the colors real quick. So we have our three additive primary colors. So I'm going to make a little Venn diagram for you to remind you how they sort of add together. So you have your green, then you have your blues. And when you have your green and your blues mixed together, you're going to get green and blue. Mixed together, you're going to get cyan. Okay. And then when you have red come into the equation, you're going to get red and green together is going to give you yellow. And then red and blue together. When the red and blue are together, it's going to give you magenta. And then when all three are together, that's going to give you white. Okay. So that is it for today. Make sure you submit these notes online and have a wonderful rest of your day. Bye.